Let's graph the rational function g of x equals x squared plus 5x minus 2 over the quantity x plus 2. The first thing we want to notice is that the degree of the numerator is 1 degree more than the degree of the denominator. That prompts us to do long division to find the slant asymptote. So let's do that. Let's put x plus 2 as our divisor. And now we're going to go ahead and perform division to find our slant asymptote. So, about how many x plus 2's does it take to get an x squared? We just need an x. Now we multiply, so we'll get x squared plus 2x. Now we need to subtract. And when we subtract here, we get 5x minus 2x. So we get 3x. Now we need to bring down the subtract 2. And we want to know about how many x plus 2's can get us a 3x. Well, we need a 3 or a plus 3. Let's multiply again. We get 3x plus 6. Once again, we now need to subtract. And notice we have a remainder of negative 8. What does this mean? This means g of x can now be expressed as x plus 3 minus an 8 over x plus 2. This is a good time to find a domain. So notice x cannot be negative 2. That means the domain of g is equal to negative infinity up to infinity. Oop, that's not true. Let's try that again. Negative infinity up to negative 2 union negative 2 up to infinity. So we got the domain of g. We could also spot out the slant asymptote. The slant asymptote is right here. So let's label that. So the slant asymptote is y equals x plus 3. Now, we're going to need some ordered pairs. Well, actually, before we need our ordered pairs, why don't we find a vertical asymptote as well? So notice for the vertical asymptote, it's going to be x equals negative 2. Let's go ahead and draw that. X equals negative 2. Have a nice vertical asymptote there. We also have a slant asymptote of y equals x plus 3. Right about there, we have a slant asymptote. Dotted. So that's y equals x plus 3. This one here is x equals negative 2. Well, why don't we find some ordered pairs? So let's make a t-chart. Let's make a t-chart of x, g of x. I'm going to start with -4. So when x is -4, let's see if we can actually find the output. So let's look at g of -4. Well, that's going to equal -4 plus 3, subtract 8 over -4 plus 2. So that's -1 plus 4. -1 plus 4 is 3. Why don't we do the same for -3? And notice we'll get 8, positive 8. Why don't we try -1? Try -1. Let's see, g of -1 is equal to -1 plus 3 minus 8 over what here? -1 plus 2. How much is that? That looks like 2 minus 8. 2 minus 8 is -6. Why don't we try x equals 0? If x equals 0, we get 3 minus 4, which is -1. That's also called our y-intercept. So we could actually say our y-intercept can be translated to an ordered pair, and that ordered pair would be 0, -1. So let's circle some characteristics. There's a y-intercept, there's a vertical asymptote, there's a slant asymptote. Now, I think we're ready to plot the ordered pairs as well. Let's try -4, 3. So there's a dot. -3, 8. There's a dot. -1, -6. There's a dot. 0, -1. Here's a dot. And why do we need these asymptotes? Well, when we connect the dots, it turns out the function is actually approaching these asymptotes. You get very, very close to them. Make sure you put arrows at the end of your graphs to symbolize that the values go on forever. So there you go. We graphed a rational function whose numerator has a degree that is exactly 1 higher than the degree of the denominator. I hope that helps.